Okay, so in this video, I'm going to cover 1.4 and 1.5. For some reason, when I was recording 1.3, it didn't quite work out, so I don't know what happened there. I have to figure that out. If I can't figure out what happened wrong to the video, I'll just cover 1.3 this Friday. But for now, we'll just have 1.4 and 1.5. 1.3 is mostly, a lot of it is on factoring these so-called algebraic expressions and an introduction to what a variable is. But all these notions should be pretty clear to us already if we've taken high school math. But again, I'll probably just go back over. I'll probably cover 1.3 during our Friday lecture. So let's start with 1.4. Let me just share my screen first. And open OneNote. So I had all these lecture notes right here. I was going through this. I'll probably just go through these notes that I wrote up on Friday. So let's look at 1.4. So 1.4 is on rational expressions. Maybe actually I'll just jump back and forth between 1.3 and 1.4 because some of this stuff does depend upon the previous section, not too heavily, but a rational expression is kind of just a fraction of two algebraic expressions. And if I scroll up here, an algebraic expression is, well, first of all, you have variables, and variables are letters that can represent any number from a given set. So it's important. I emphasize the set because, well, it's the reason why we covered sets in the first video, because they grow increasingly more important. The notion of a set, that's really all mathematics is you're dealing with sets and functions, which we haven't covered, but mathematics is really just about sets and functions on sets. So a variable is a letter that can represent any number from a given set, and we usually use x, y, w, and z to represent some variable or represent some number. And then when you take combinations of variables and real numbers using addition, subtraction, multiplication, division, powers, and roots, you obtain algebraic expressions. So I gave a couple examples. You had 2x squared minus 3x plus 4. You could have something like square root of x plus 10, or you could have y minus 2z over y squared plus 4. And then very important ones were monomials. I guess I'll just go over 1.3. It's not that bad. I don't have to write as much. I don't have to rewrite this. So that was the part that took a lot of time. So polynomials are very important. Important subclass or subcollection of algebraic expressions. And they come in three basic, well, there's three particular types that we'll deal with, but there's a more general notion of a polynomial. So polynomials can come in monomials, which are terms of the form a to the nx, where a is a real number. Sorry, let me see. Where's my cursor? So a is a real number and n is a natural number. So 1, 2, 3, 4 up to infinity. Binomials will be sums of two monomials, so two things of this form. And then trinomials will be sums of three monomials and higher number of terms. We don't really generally give names to higher number of terms. I'm sure you could, but we won't. And so, but more generally, a polynomial in the variable x is an expression of the form an times x to the n plus an minus 1, x to the n minus 1. And then you have these intermediate terms, which I denote by ellipses or ellipse. I don't know what the correct term is. Anyway, so you have a to the n, a sub n, x to the n, and then these intermediate terms, and then a1x plus a0, where a0, a1 up to an are real numbers, and then n is some natural number. This right here is called the leading, or this is called the constant term. And so if this a to the n term right here, this is called the leading coefficient. If this is not 0, then we say the polynomials of degree n, and a to the n is the leading coefficient. The monomials that comprise this polynomial are called the terms of the polynomial. So we can have in the video I mentioned why polynomials are important, because they really, when you get to calculus, they're really the only things you need to worry about, because it's in some sense, in calculus you deal with continuous functions, these functions whose graph you can draw without lifting your pen. That's just one intuitive characterization of continuous function. And you do various things with these continuous functions. You take derivatives of them and you integrate them. Derivative gives you like a rate of change. So maybe your function is a function of time, and it'll give you the position of a particle at a given time. If you take the derivative of this, you get the velocity, and if you take the derivative of the velocity, you get the acceleration, etc. And you can only take derivatives of continuous functions, but the derivative gives you a notion of a rate of change, and the integral gives you the notion of an area. Although for integrals, you don't really need the function to be continuous. It just has to be, in a certain sense, nice. But the nice thing about continuous functions actually is that they can all be approximated by polynomials, these more basic functions, these basic algebraic expressions. So you could have some very complicated functions, and just so long as they're continuous, you can approximate them by polynomials. And a way of saying this is that if you look at the space of all continuous functions, so you have this abstract space, and each point in the space, so this will be an infinite dimensional space. If you take each point in the space will represent some function. What this says is that if you look at all the points which represent polynomials, they're somehow like really diffuse in the space. They like really fill up the space. You say that the polynomials are dense in the space of continuous functions. That's a really concise way. It sounds abstract and difficult to parse, but it's a concise way of expressing the fact that all continuous functions can be approximated by polynomials. So the polynomials fill the space of continuous function, or diffuse in it, in the same way that rational numbers fill the space of real numbers, or are very diffuse in it. So if you take any two real numbers, between them you can find a rational number, and you say that the rationals are dense inside the real numbers. So the density of the polynomials in the space of continuous functions is the same as, or it's like the density of the rational numbers in the set of real numbers, or the space of real numbers. So that's what we mean. And so studying polynomials is very important. So let's just look at some more things we can do polynomials. We can add and subtract them. So in the first video, I forgot to mention constant terms, which I just did not too long ago, but 4 is a constant term. So this is example 1 of part A. And because a variable x represents a real number, the variables will satisfy the properties of real numbers. You have addition, you have commutativity, you have associativity, you'll have distributivity of numbers. You can distribute these numbers. And so when we add polynomials, we want to combine, so we want to associate Well, the procedure is that you have these two polynomials. So you have, and I bracketed them off with parentheses. We have this polynomial, and then we have this polynomial. So we start with this polynomial on the left, or you can start with the one on the right, and you look at the highest degree term. So that will be x cubed. That is the largest power of x in this polynomial, this expression. And then we look over here at the corresponding term. Or we look for the term whose degree corresponds to that, and that's x cubed. So we'll have these two x cubes, which will associate together, and the coefficient of each one is 1. And then we start with the left polynomial again. We look at what's the next highest power, that's x squared. So the coefficient of that is -6. And now we go over to the polynomial on the right, and we ask ourselves, is there an x squared term over here? Yes. So we put these together. So we put the x cubes together. Now we put the x squares together. And now we're going to put, now we're going to just continue this process. We have x to the first power in the polynomial on the left. And we also have x to the first power here. So we put these together. So we have 2x minus 7x together. And then the polynomial on the left has a constant term, but the polynomial on the right doesn't. So we just put the 4 by itself. I circled this because this step isn't strictly necessary, but I'm just illustrating to you the fact that we're using distributive properties and factorization properties of real numbers because x represents a real number. So we can factor out the x right here. We can factor x cubed right here. So we get 1 plus 1 times x cubed. We can factor out the x squared here. We get this. We can factor out x to get this. And then 4 is just by itself. And then we can combine the coefficients. So that's, this step isn't necessary. And maybe even this step right here isn't strictly necessary, but I just want to illustrate to you what's going on. Really what you're doing is you're just adding the coefficients together. You're like matching up you're looking for the x to some power in the one polynomial, and look to that x to the same power in the other polynomial, and you're just adding the coefficients. That's what's going on. So this is just the foiling, which we're all familiar with. So we want to multiply algebraic expressions, and foiling, as I said, is something we're familiar with. And how you prove that is just by using the distributive property twice. So if we call this right here E, then what we can do is we'll have E times C plus D. We can distribute that. So we use distributive property. And then we substitute in A plus B for E, and we use the distributive property again. And then we use the commutativity of addition to get to this last line. And we have this foiling rule, which I'm sure we're all familiar with. We learned somewhere in school. I don't know exactly where. I was homeschooled, so I don't know what exactly you learn in public school and the sequence in which you learn it. So I'm sure at this point we're all familiar with foiling. All I wanted to do is just point out how do you prove this rule, because that's what modern mathematics is about, just proving things now. And then also point out that because, again, x is a variable, it represents a real number, so we can use these foiling properties. And then I illustrate that fact in example 2. So we just do this foiling here. You do 2 times x times 3 times x to get 6x squared. Then you do 2 times x times -5 to get -10. And you just keep going through and you get this as your final answer after you simplify. And we can do something a little more complicated. So this example 2 is a product of 2 binomials. In example 3, we have a binomial times a trinomial. And we're just going to use the distributive property. So we'll do 2x times this whole thing in parentheses. So 2x times this whole thing in parentheses right here. And then similarly, we're going to do 3 times this whole thing in parentheses here, so to get this. And then we use the distributive property again. And when you do that, you get this long expression here. And I'm just gonna order the terms in according to the largest power of x. So x cubed appears only once in this line. So we'll just put that at the front, and then we got to match the corresponding powers. So we have x squared here, this 10x squared, and we have 3x squared here, so this x squared. So we put those together to get negative 7x. Then we have x terms, we put those together. I put a bar above them to distinguish them from the x squared terms. So we get negative 7x, and then we have this constant term 12. And then for this one, this is the last, I think, distributing one. I just wanted to go over this one quickly. So you have, just because it's not a polynomial, it's got this radical, which may throw some people off. You just go through the same procedure of foiling. So you give 2x times 2x to get 4x squared. And then you do, so you did the first ones. I guess I do foiling a little differently. I don't know. I do the first times the first, and then the first times the last. So I guess this is not foiling, but that's okay. It gets you the same result. And then I do the last times the first. So the first times the first gives you this 4x squared. First times the last gives you negative 2x square root of y. And now the last times the first gives you negative 2x minus y. And now the last times the last gives you negative y square root of y times square root of y. I guess I do this foiling in this way. That's not really foiling, but I multiply in this way because it puts together the terms that need to be associated automatically. We have these middle terms that will cancel out. But if you did like traditional foiling, it would have scrambled up all the terms, and you'd have to rearrange them. But so this shows you that, clearly shows you that these middle terms cancel, and then square root of y times square root of y just gives you y. So now we're going to look at factoring. So we just factoring is just distributing in reverse. So it's not much different than what we've been doing. So we have this polynomial in two variables, and we want to factor it. So the first thing I do is I look at the coefficients of each term in the polynomial, and I ask what's the common factor. In this case, it's 2, so I can factor out a 2. And then this, if I factor out 2, I get this line here. So you have 2 times this whole expression. You can see I factored out the 2 from the coefficients. And the next one, I had to ask myself, what's the next? Now I want to look at the variable terms. I want to factor out some variable terms. And I need to ask myself, what's the common factor for these? So they each one has an x, but what is the largest power of x I can factor out? Well, I can't factor out a power of x to the 4th, or I can't factor out x to the 4th because if I do that, then they'll introduce a negative sign here and a negative sign, or it will introduce a negative exponent in these other terms. So I don't want to do that. I can't, and the same reason I can't factor out x to the 3rd because it'll introduce a negative exponent here. So really all I can factor out is x. And this, likewise, I can't factor out y to the 3rd or y to the 4th for the same reason, because I'll introduce negative exponents, and I don't want negative exponents. So I can only factor out y squared. So if I do that, I get 2x y squared, and then in the parenthesis I get this, and that's the answer there for that one. So now we want to factor out, so these are all special cases of factoring. So the factoring a trinomial of this form. So these split up into two cases. You have this case where your leading coefficient is 1. And just as an aside, things of this form, alpha times x plus beta, where alpha and beta are real numbers, are called linear factors. So I want to factor these trinomials into linear factors. So example 7 is x squared plus 7x plus 12. And let me just erase what's going on here. So the idea is we want to fill in these blanks, and I obviously saw what the blanks are, but let's just go through this anyways. So when we multiply, we want to factor this into two linear factors, because if you have the factors have to have a degree less than the thing being factored. So this is a second degree polynomial. So that means its factors have to be first degree or 0 degree. In other words, constant numbers. So they have to be linear factors. So it has to be something of this form right here. Now, we can't have a coefficient other than 1 attached to the x, because if we do, when we FOIL, we won't get this x squared here. So that's why we have to, we know right off the bat that we have to have x's here. The only thing that remains is, what do I put in these blanks? So if you can remember the foiling process, we need to put blanks in here such that when you multiply, we need to put numbers in the blanks such that when you multiply them together, you get 12. But when you add them, you get 7. So to do that, we want to put some restrictions on what those blanks can be. And we have already just stated one condition they must satisfy. They have to be such that when you multiply them, you get 12. So what we need to do is look at factors of 12. And so I wrote these in this pairs. So there is another pair. There's 1 and 12, but we can rule that out immediately, because when you add 1 and 12, you do not get 7. So all that remains is 2 and 6 and 3 or 4. But if you add 2 and 6, you get negative, or you get 8, which is not 7. But if you add 3 and 4, you get 7. So that tells us that what goes into these blanks are 3 and 4. So the idea is, when you factor a trinomial, you want to look at least when you're in this case, when a is equal to 1, all you have to do is look at this term right here, look at its factors, write them in pairs like that if you need to, and then ask which ones sum to the middle term. And once you do that, you can just rule out what pairs aren't allowed. So now we have the case. I'm not going to go through this example because I don't want this video to be too long. We have the a equals 1 case, and that's it's still the same procedure, except now we have to put blanks on the x. What's the coefficient of x? But we have that, so we have to play the same game with this term right here. We have to look at factors of this, but we also have to look at factors of this, because we want coefficients here such that when you multiply the outer terms, you get x squared, but you want the coefficient to be 6. So you have to look at factors of 6, and these are the only factors of 6. 6 and 1 and 2 and 3. For this one, you have 2 pairs, because the sign matters. And what you're going to do then is you're just going to consider these pairs together and find the one that fits. So you'll say, okay, I'll start with 6 and 1. All right, if I put 6 here and then 1 here, now I'm going to pair 6 and 1 with -5 and -1. So I'm going to put -5 and then 1. And then you ask yourself, okay, if I multiply these two together, do I get this expression on the left-hand side? If I don't, then you got to cross out that combination. So you know that this can't be paired with this. So then you go ask yourself, okay, well, can this right here be paired with this one? And then you fill in the blanks with those numbers. And if that doesn't work out, then you rule that out. And you just keep going through all the combinations until you arrive at the right one. I'm not going to go through that though, because I'm running out of time, and actually I have my own class I have to attend in a little bit. I might have to pause this and then record afterwards. So one formula you should remember, I don't really insist on remembering formulas because it's not helpful, but one that you should is this difference of squares. It's easy to verify. You just, so the formula is a squared minus b squared. This is equal to a minus b times b plus a plus b. If you distribute this side, you'll obviously obtain this side. So this is in fact equal. And here's just an example illustrating how you do this. So we want something squared minus something squared. So we don't quite have that. We have this x squared, which is good. That's a good first, that's a good start. But we also should note that this coefficient in this constant term can also be written as squares too. 4 is the same as 2 squared, and 25 is the same as 5 squared. So this gives you this line here, but then when you go down to the next one, you remember powers exponents kind of distribute. So I can pull this exponent out here, and I'll have 2x squared minus 5 squared. So a will be 2x and b will be 5, and then I just apply the formula. So now this is going to be the last thing I'm going to cover, and then I'll move on to section 1.4. So factoring expressions with fractional exponents. So this one's a little tricky because before, when we had integer exponents, we wanted to factor out the largest power. But in this case, we want to factor out the smallest power, and it'll be clear when we go through an example why you want to do this. So this is example 14a. So the example asks you to factor this expression 3x to the 3/2 power minus 9x to the half power plus 6 to the negative half power. So the smallest power of x that appears in here is x to the negative 1/2. And also we got to look at the coefficients. Remember, that's the first thing you do. Look at the coefficients. They all have a factor of 3, so we can factor out 3. Now, when you factor out x to the negative 1/2, what powers, we need to figure out what these powers should be. So we got 1 here, x to the first. Well, the way to do this is that, well, you need to put a number here and a number here, such that when you distribute the x to the negative 1/2 back through, you get this power, and then you get this power back. Well, if you put a 2 here and you distribute x to the negative 1/2, remember you add exponents. So 2 minus 1/2 is 3/2, so it gives you 3/2 back. And if you distribute the x to the 1/2 over here, you add exponents. So when you do 1 minus 1/2, you get the 1/2 here. And you don't have anything here because you factored out that x to the 1/2. So you got to factor out the smallest power first, and then ask yourself that question: what number do I need to put on these x terms? What exponent do I need to put it on, such that when I distribute this back through, I get these exponents? And I'm just gonna pause the recording here. Or I'm gonna try. So let me stop sharing, and then I'm gonna pause the recording. Okay, so let's pick up in 1.4. Let me share my screen again. Hopefully this works, because last time I did not share my screen and I spent a whole hour recording and nothing came out. So it says I'm recording, sharing my screen, okay. And it's recording, right? Recording to the cloud, okay. In some respects, being virtual is not fun at all. So 1.4 is on, so we talked about algebraic expressions. Now we're going to talk about rational expressions, which are just fractions of algebraic expressions, essentially. So yeah, let me just write that down. So these guys are fractions, quotients of algebraic expressions. So for example, I have something like 2x. Well, I guess we already saw some of them. We saw one example in the first section in 1.3. of a rational expression. We're going to just localize in this case, though, to specifically rational expressions. So these are some examples here: y minus 2 over y squared plus 4. And then you could have something like x over square root of x squared plus 1. So because x can represent a number from a set, we have to be careful about what set we're talking about. Have to be. So let me just, x represents a number from a set. So have to be careful about what that set is. And this is where the notion of a domain of an algebraic expression comes into play. So domain of an algebraic expression, which includes these rational expressions, is the set, maybe you want to take the largest set of numbers. Hold on. Largest set of numbers that we can plug in for x. So for example, we can't have, with respect to rational expressions, we can't have division by 0. Division by 0 is not permitted. Or with square roots, we can't take this, because we're dealing with real numbers, we can't take the square root of a negative number. So this puts restrictions on what x can represent. So for example, polynomials have domain. Now for polynomials, there is no restriction. So the set is all of R. So x can be any real number in a polynomial. So for example, we have like a polynomial is something of this form. We can plug in any number of x for this into this. There's no restriction. There's no problem with that. But what about something like this? Well, we know we can't have, we can't just plug in any number, because we can't take square roots of negative numbers, and we can't have division by 0. So that immediately puts a restriction on what x can be. So the domain of this is going to be, there's a lot of ways of expressing this. So we could say the domain is the set of all real numbers. Remember, this is set notation. So the set of all x real numbers such that x is greater than 0, and it's important, this condition also has to be satisfied. X is not 5. And remember, ands correspond to well, I won't get into that. There is some intersection going on. But so this is one way of expressing the domain of this expression right here. So the numerator and the numerator is square root x. We can't have square roots of negative numbers. So that condition, this condition handles that. And we can't have division by 0. So x can't be equal to 5. So this condition handles that. So jointly, these two conditions can get together, guarantee that I can plug in any number to this expression, provided they satisfy these two conditions. So this set is also equal to, it's also equal to the following. It's equal to 0, 5, but not including 5, union 5 to infinity. So these two sets, this set here, these sets equal each other. If you think about this for enough amount of time, if you think about this long enough, you'll see that these two sets are equal. They're two ways of expressing the same set. So this is the notion of a domain. The domain is of an algebraic expression is the largest set of numbers that one can plug into the expression 4x. So when we what is it? Well, that's just one aspect of this. The next section is kind of a jump. It's kind of a detour, I guess. But we want to look at, so this is just one aspect of rational expressions, this domain business. This is the more abstract part. Maybe you haven't seen something this idea of this before, this idea of a domain. But now we're going to go maybe discuss something more familiar. We're going to look at simplifying rational expressions. So the simplifying rational expressions really comes down to the fact that this equation holds. So we have an expression, AC, rational expression AC over BC, and the numerator and denominator have a common factor of C, so we can cancel them out. And so that's really what simplifying rational expressions comes down to, using this fact right here. So let's look at an example. So we have x squared minus 1 over x squared plus x minus 2. So we want to factor. To simplify this, we need a factor. So the numerator is the difference of two squares, because, right, remember, one is equal to 1 square, right? So we can factor the top like so, and the bottom can be factored as, so remember, you know, if we use that method in the first section, or 1.3, section 1.3, we need to look at, so we have a 2 here. This is a 2. We need factors of 2 such that when they sum together, you get 1. The middle term, you get the coefficient of this middle term right here, which is 1. So if you think about this long enough, you'll see that it's just going to be 2, so plus 2, and then minus 1. And if you FOIL this, you'll see that x squared, x times x gives you x squared in the denominator. Then you have x times -1, and then you have the 2x. So you have 2x minus 1 will give you that middle term of just x. And then the outer terms, 2 times -1 gives you the -1. But we see that we can apply this equation right here, because we have this right here, these common factors in the numerator and the denominator. So we cancel those out to get this. So now that's an example of simplifying rational expressions. Now let's look at multiplying and dividing rational expressions. I'm just going to do multiplying. Well, let me just not say anything so as not to get ahead of myself. But this is multiplying and dividing rational expressions. And again, it comes down to a simple rule. When your rational expressions will be of this form. So you have this multiplication in the middle, and you just simply multiply the numerators by the numerator by the numerator, and the denominator by the denominator. So let's look at an example. We want to perform, this example asks us to perform the indicated multiplication and then simplify. So we have x squared plus 2x minus 3. And then we have x squared plus 8x plus 16 times 3x plus 12 over x minus 1. So the first thing we're going to do is, well, this fraction right here cannot be simplified. It can't be factored any further, but this one certainly can, the first fraction. So we're going to factor that. So if you factor the numerator, you're going to get x plus 3 times x minus 1. And if you factor the denominator, you'll see it's not hard to see that it's going to be x plus 8, or sorry, no, I'm sorry. It's going to be x plus 4 times x plus 4. But we can just keep that as x to the 4 squared, right? Now in the numerator, actually we can factor. In the numerator, factor the numerator of the first fraction. That will be, we can factor out a power of 3. So that will give you 3 times x plus 4 over x minus 1. Now using that rule above, we just multiply corresponding numerators and denominators to get x plus 3 times x minus 1. And I'm going to put the 3 in front here, times x plus 4. That's the numerator. And then the denominator, we're going to have x plus 4 squared times x minus 1. And now we can simplify. So this will cancel with this, and this will cancel with that power right there. And what we'll be left with is 3 times x plus 3 over x plus 4. And to divide, so now we looked at multiplying rational expressions. To divide, expressions, we just use this rule. It basically reduces down to just multiplying the rational expressions. So you might have something of this form: a over b divided by c over d. And to do this, you just simply invert the second fraction. So you have a over b, and that when after you've inverted, the division will become multiplication, and you get d over c. And then you just multiply those, as we did above. So I won't go through an example because it's basically going to be the same thing as the case of multiplication. Now, let's go on to adding fractions. So, or adding and subtracting, but again, subtraction reduces, is just a special case of adding. So again, we have a rule. So it says when you have two fractions with the same denominator, the way you add these fractions is simply by adding the numerators. Now, we're not always going to be given two fractions with the same denominator, so we have to do this process of finding a least common denominator. So let me look at an example, or let us look at an example of this. So 3 over x minus 1 plus x over x plus 2. Again, so now we don't, in this example, we don't have the same denominator, but we can find the least common denominator. And the way to do this is just to take the product of the two denominators and multiply, the product of the two denominators will be the least common denominator. So we just got to manipulate these fractions a little bit. So we'll multiply the first fraction by x plus 2 over x plus 2. And then the second fraction will multiply by x minus 1 over x minus 1. And you'll see that this does indeed give us two fractions with the same denominator. So we get 3x plus 2 over x minus 1 times x plus 2. And then we get x times x minus 1 over x minus 1 over x plus 2. So they have the same denominator. And now I'm going to distribute and then add. So we get 3x plus 6 plus x squared minus x over x minus 1 times x plus 2. Now we're going to combine terms. So we have x squared. So 3x minus x, so it'll give us 2x. And then we have this constant term of 6. And the denominator will have x minus 1 times x plus 2. And the subtraction is basically the same, so I'm not going to go through one of those examples. Let's see, so we have, let's see what else. Let me see. I need to stop sharing for a second. Let me share my screen again. Okay, so just a few more things, and then I'm not going to go over 1.5 because that's actually only really one thing I want to go over from 1.5, and I'll just do that on Friday. So another type of expression you can encounter is the so-called compound fraction. So compound fraction is something of the form, that's a fraction within a fraction. So for example, you could have something like this, and you might be asked to simplify this. So one way of dealing with this is to sort of look at the numerator and denominator separately. So this is you have a fraction plus 1. So we want to add these together to get a single fraction. So we want to find a common denominator for each, the numerator and the denominator. So we'll just do that. We'll do that now. So to do that, so you just want to deal with the numerator and denominator separately. And so to add to simplify the numerator, we have to change 1 into y over y. So now we have something that has the same denominator as the fraction x over y. And we want to do the same thing to the 1 in the denominator. We want to convert it into something that's a fraction and has the same denominator as y over x. So we'll change 1 to x over x. And now we can simplify the numerator and denominator. So the numerator will be x plus y over y, and the denominator will be x minus y over x. Now this is the same thing as x plus y over y divided by x minus y over x. But we know by that rule, division is just, you have to flip the second fraction and then multiply. So we'll have x plus y over y times x over x minus y. And if we multiply those, we'll get the numerator by the numerator and the denominator by the denominator. We'll get x squared plus xy over xy minus y squared. so I guess you can maybe have factored out that. It doesn't matter. That's one way of simplifying. And let's see, what else? We've sort of seen this already, but I guess I'll just go over this one last example of rationalizing. This one example of rationalizing the numerator, say. You could be asked to rationalize the numerator or the denominator, and it's basically the same procedure. So we'll just do this one, rationalizing the numerator of an algebraic expression. So for example, you might have 4 plus h minus 2, so square root of 4 plus h. And we want to rationalize this. So this is important actually in calculus because it'll help you compute derivatives. So this is an important concept actually. So rationalizing is you have to multiply by the so-called conjugate. Conjugate, or it's actually called conjugate radical. And that is obtained, well, first of all, when we want to multiply by 1 in a different form, because we don't want to change this. We want it to be, we want to change it into something that's an equivalent expression. So we don't want to change anything. So we have to multiply it by 1 in a clever way. And the conjugate radical of this thing in the numerator is simply obtained by changing the sign to its opposite. So you have square root of 4 plus h plus 2. And then you have to also divide by this because this will give you 1. This fraction right here, this is just 1 in a clever written in a clever way or a different form. So when you multiply the numerators together, this should just remind you of difference of squares, right? It'll be, when you multiply the two numerators together, you'll get this first thing here squared minus this squared. Well, when you square a square root, you just get the thing under the square root, which is 4 plus h. And then you're going to subtract off 2 squared, which is 4. And then the denominator, you're going to get h times, you're going to multiply the denominator. So you get h times root 4 plus h plus 2. And then the 4's will cancel out in the numerator. So you get h over h times, so h over h times 4 plus h under the square root plus 2. And then these h's cancel out, you'll get this. And then you're literally one step away from calculating the derivative, actually. So to get the derivative, so let me just point this out as a side. Derivative of expression, what is it at? I guess it's at 2, maybe, or something like that. Don't quote me on that, but this part's right. You just take this so-called limit. You take the limit of this thing right here as h goes to 0. But if h is approaching 0, then the idea is that this is a continuous function, which I haven't really discussed, but that doesn't matter. We have an intuitive idea what a continuous function is. When h goes to 0, like it's just getting we say it's getting arbitrarily close to 0. And it will just eventually become 0. So when you do that, you just plug in 0. Now, limits like this don't always work out that nicely, but taking the limit as h goes to 0, in this case, just amounts to plugging in 0 for h. And then this will give you, you have square root of 4 with 2, so then you'll get 1 over 4. So that's the derivative. So that will give you the rate of change of this function at 2. This will be the derivative. And, you know, derivatives have importance in basically all the sciences, basically, you know, engineering and physics. So this kind of calculation is important when you go to calculus, when and if you go to calculus. So this, I'm going to just stop here. We'll start when we start on Friday. I'll ask if anyone has questions about the video or anything else, and then we will I'll just briefly go over 1.5. So I will see you Friday.